Hi, and thanks for tuning in to the CBA Podcast, a place where we chat about our own recent achievements in the area of electronics, software and mechanical engineering, and more likely than not, give excuses for not having done anything at all. Hello and welcome back finally to another episode of the CBA Podcast. I think this is the first podcast since 14 months, and in the description of the show, if you look at the webpage, it says semi-bi-weekly podcast, so that's once every 14 days. So it's only a factor of 30 below that, but no big deal. So I hope you're all in good health. I think during the Corona period, or at least what I call Corona period, last couple of years now, the downloads have been 3 times as much, so that's good. But on a more serious note, I hope you're all in good health, and thanks for tuning in again. So, what to expect in this episode? You would think it's been 1 year, so there's 1 year worth of stuff to talk about, but sadly that's not the case, or happily that's not the case, whatever way you choose to look at it. Someone else mentioned it's probably a good idea, and I did that in the first couple of podcasts, I think, to go over the sections at the start of the podcast so people know what to expect in a summary. So let's do that right now. First, there's a section about failure, of course. There's always failure. Some small things that I ran into. Next up, there's a couple of small tips and small things that are so small they don't deserve their own detailed story. So let's put them all in one big section. Then some environmental stuff. Next up, some homebrew stuff I did. Maybe interesting. Then some more environmental stuff, that is the fuel consumption of cars. Now, I'm not a big car guy, or don't know a lot about cars. Actually, I don't know anything about cars, so this is basically me reading off Wikipedia and reading off the internet. But it's about fuel consumption of cars and how to save a bit of fuel in a very logical way, and how to enjoy the ride more and enjoy the scenery more and stuff like that. So that's that. Next up is a small handheld scope I finally bought. And finally there's a vacuum cleaner I took apart. Tried to fix it, I failed at it. But I found some semi-interesting stuff inside electronic-wise, so let's talk about that a little bit. And once more, if you have suggestions or comments or rants or complaints or whatever about the podcast or the form of the podcast or the topics talked about or the way in which they are discussed or not discussed, you can mail me, and the email address or feedback address is on the podcast.cba.si webpage. It's probably in the show notes and probably from the place where you got this podcast. So take a look at that if you're interested, and let me know what you think. First up, some failures. When you order PCBs for your project, you can get them back in a panel. So that's multiple PCBs on one big plate. So you can assemble them and then break them out later. It's easy. And the way the PCBs are separated in the panel is either through V-scores, for example. So they make a shallow cut in between PCBs so you can break them off later using a tool or using your hands. Another way is using mouse bites. So basically they mill the outside of each individual PCB and attach it to the bigger panel plate using mouse bites. That's break tabs basically. So they leave a little bit not milled and they drill very small holes through it so you can break it off at that point. You can break the individual PCBs out of the panel plate. And of course it doesn't work if you have to place a component on your individual PCB there that overlaps the edge a little bit. In my case it was a USB connector. So tip for me and for you and for everyone maybe. Put a description in the Gerber files or in the PCB outline files. Don't put mouse bites here or something like that. Or even better, design your own panel, but I'm usually too lazy to do that. So I add a description in the Gerber file, and that usually works. Another thing was hydroscopic Pcbs. That's PCBs that are basically PCBs suck up water over time. So if you leave them laying on a shelf and for half a year or something like that, they suck up water. It's not a big deal until you put them in the oven. What happens in a reflow oven is temperature is ramped up relatively fast. So the water inside the PCB basically starts to boil and starts to expand into gas. And then it basically destroys the PCB from the inside out. So I think I talked about that, or we talked about that some previous time. In that case, it was LEDs, and the lens of that was also hygroscopic and had sucked up water, went in the reflow oven and basically destroyed the LED. And if you can see it, that's pretty easy, so you can replace the LED. If you cannot see it, you basically have to find a bug, have to find a fault and then replace it, so it takes a lot of time. So here's a quick tip for you. If you have a PCB that you have put in a reflow oven, and you take that PCB out of the reflow oven after it's soldered, and you see components in places that are not meant to be there, components that basically jumped off the PCB and landed somewhere else, either inside the reflow oven or inside some other location of your PCB, don't just ignore it. There's something wrong there. There's gas inside the PCB, and moisture has expanded, has basically blown the component off the PCB and it landed somewhere else. So that's a big indicator of something going wrong. And it's not just a component, but if there's inner layers in the PCB, they may be shorted or they may be open. So basically the PCB is scrapped then. So maybe a tip for you. It went wrong here once, and takes a long time to find that fault. So maybe a tip for you. And here's basically a reminder for future self. If you have a PCB with intelligent stuff on it, for example, microcontroller or logic device or some memory device even, and that device has programming pins in order to program it after the PCB has been assembled, and if you can, please leave those pins dedicated to programming and nothing else. And if you must combine them with operation of, for example, a microcontroller because it doesn't have enough pins, then beware of the direction during programming, and also beware that, for example, you don't want to put a big capacitor on a clock pin on the programming interface because that doesn't usually end well. And also if you have jumpers or something like that attached to the PCB, then beware that maybe you have to take off this jumper while programming it. And that was exactly what happened in my case. I didn't have enough pins, had a pin dedicated for a jumper selection, and was wondering why it couldn't be programmed because the jumper was still mounted and it pulled the pin to ground. So maybe a tip for you as well. And finally, something I ran into myself as well with a PCB I designed a while ago. Maybe you, or in this case me, wants to keep mechanical components of your PCB, for example connectors, where users apply force to the PCB away from sensitive components. So in my case, it was a 5mm relay. That's a plastic relay, signal relay, sitting quite next to a connector. And users, they don't have enough time or something like that, or they don't know exactly how to do it, or they don't know what's sensitive and what's not. And that's fine. But sometimes, for example, they use the relay to get a good grip of the connector or something like that. So they push the relay with force so it doesn't work anymore. And that's a strange bug to find. So can maybe save you a little bit of time when you separate sensitive components from heavy-duty electromechanical components. Another little side note, I noticed that I'm struggling now with recording itself. Not so much the technical aspect, but me. So I'm sitting down or standing up while talking, seeing what works best. And I remember these are things that I struggled with as well when I recorded more frequently in the past. So we'll see how this goes. Now onto the small things, small tips. I'll try to keep this really small and short because there's not a whole lot there. First is an online circuit emulator. That's www.falstad.com, spelled FALSTAD.com. I think the guy who makes it is called Paul Falstad or Falstad, probably butchering the name. Sorry, Paul. It's quite intuitive. You can drag and drop components onto your worksheet, components and probes and sources, power sources, and then simply start the simulation and indicate what you want to measure, current or power or voltage or whatever, and then you see a nice graph, and you can see current flow. That's also nice. You can see little electron balls, and you can see the electrons flow. Let's say that. And I even use it for work a couple of times. So beware, of course, this is a simulation, obviously, and I like to compare this to traffic. So if you're in traffic and the light is green, doesn't mean close your eyes and straight ahead. Still, use common sense, and there may be bugs there somewhere. Some really small tips may be useful for you. If you have bright LEDs that you're testing, you can cover these with a piece of paper. Simple printer paper will do. Because once your eyes saturate, at least that's what I call it, you cannot really notice the difference between intensities. So if you lower the intensity by covering it with a piece of paper, you can see the differences more clearly. And also, if you've been staring into an LED and then staring onto your screen, you know what I mean. That's your eye is like not working for a little while. Next up, there's hot glue. I probably talked about that a few times. It's one of my favorite tools to use while prototyping. And you can use that to diffuse light. So you can put it around the LED or fill a compartment with hot glue and then place an LED inside that, or place your PCB with LEDs inside it. And the glue is not transparent enough to, it's milky. So it will diffuse the light quite well. So maybe a tip for you. I made a little prototype here, and I intend to make a little prototype with a compartment indeed filled with hot glue, and then placing a PCB inside it, and then basically lighting up the whole compartment without seeing the PCB anymore. Anyway. And another thing that's quite sad, actually, that I noticed this only now, if you have a PWM input and you don't have a PWM output, you can simply mimic 0% and 100% intensities by connecting the input to ground or positive voltage rail. And it's sad that I only noticed that now. So if you want to comment how sad that is, you can mail to the email address on the podcast.cba.si page, and we'll discuss it. And we'll listen to your grief and your comments and your rants and your complaints. And one thing that I find a little bit mind-blowing, at least, is, let's say you're selling a toy in batches of 1 million, and one engineer finds a replacement component that is 1 cent cheaper than the original. So that would mean 10,000 euros profit in total per batch. Now, to use that component, you can justify maybe 5,000 euros of engineering work to change the layout, to use a new component and still make a profit. I find that a little bit insane. So these are not numbers I usually work with, but still, I'm sure toys are sold in the millions these days. And then an actual question for you, listeners. I recently came across a PCB that had on each via the solder mask was left off. So you saw the bare copper on each via. And I'm wondering why that is. So one thing I can imagine is if it goes through a wave soldering machine, the uncoated via picks up solder. So the connection between the top and bottom of the PCB becomes better because there's solder inside the via. But it didn't go through a wave soldering machine. This was pure SMD. So I'm wondering why is that? Maybe to put it uses a test pin or something like that, or programming. But then again, I wouldn't put a programming probe inside like a pogo pin inside a via. Maybe you damage the via or something like that. No idea. So if you know why that is, then please let me know and discuss it next time. Now, another thing. Recently I'm a little bit more aware of the environment. Try to be a good boy and take care of the environment, so create less waste, for example. Now, one way to do that, maybe also a tip for you, and it's actually quite fun, is to recycle stuff, to bring it to the second-hand market, to the thrift store, for example, so they can either fix it or simply sell it off, and the profit goes to charity or do whatever. But people can use the stuff that you would normally throw away, so I usually take all my stuff to a thrift store. Over here, there's also some places where you can hand in broken tools, for example, hand tools, but also electrical tools. And people there, they will fix it. They're volunteers, and they'll sell it off to either development countries or people who can actually use the tool. So you create less garbage. That's good. And talking about the waste, laser cutting plastic, how about using square shapes more than round shapes? Because you have a whole lot of garbage, I noticed. I'm looking behind me at a whole stack of acrylic plates with round stuff lasered out of them, and remaining plate is something I can't use, so that's basically plastic garbage. So square rather than round, please. I hope that wasn't too preachy, but anyway, if you don't like it, please send comments or feedback to the podcast. You can find the email address on the CBA podcast website, which is podcast.cba.si. Yeah, so here's some homebrew stuff I did. It's not too much. I think last time, or at least some previous episode, I talked about a light decoration thing I made, where you can place acrylic sheets, laser engraved acrylic sheets into some base, and light would shine into the sheet, and then you can get a nice effect. I made a few more of these, sold a few more of these even, and to assemble the base with the electronics inside it, which is also made of acrylic sheets, I made a little assembly jig, also made of acrylic sheets. And I made a little video about that, so you can actually use a laser cutter to assemble stuff that's been laser cut. And what I did was use glue to glue different stacks of acrylic against each other. So maybe if you're interested in that, take a look at the video, and it works quite well. Now, something I fixed here was a lab power supply. This is a Corad, or how to pronounce it, KA3005B programmable DC power supply. And the problem was it has an encoder wheel to adjust the voltage and the current limit, for example. And this encoder would skip digits, so it was very jittery. Sometimes you move the wheel forward and the number on the display would go back, for example. Now, the fix was to replace RC filter after the encoder with a new cap, new ceramic capacitor, 4 nanofarad, 100 nanofarad instead of 4.7 nanofarad. Did for you, maybe, or at least for me, and it worked out very well in my case. If you have some intelligent stuff to process pulses coming from a device, or push buttons, or in this case an encoder, please do the debouncing in software and not in hardware, because I don't think it ever works. So if you don't agree, please leave a comment, and so on. I'm sorry to say I don't have photos about the power supply fix or where to put the capacitor on the PCB, because a couple of days ago my telephone got stolen and the pictures were on there. And I'm too lazy to open the supply up again and see where I soldered. So that's about the quality level you can expect from this podcast, and you knew it. This is episode 44, 45 or something like that, so if you didn't know by now, you're a slow learner. I also took a look at the glucose meter for people with diabetes. I think it's called a glucometer. In my case, I don't have diabetes myself, but someone in my immediate vicinity does. So each measurement goes as follows. You have an electronic device, basically a calculator, and you have disposable flex PCB strips of about 3 by half a centimeter. And you stick one of these strips inside the measurement device, then you prick yourself and finger, probably. Some blood comes out, you soak the tip of the flex PCB in your blood. The blood wicks into the flex strip, and then you do a measurement, and the device indicates if the measurement is valid, and if so, what your glucose level is. Now, this flex strip, I'll post a picture of that, a scan of the flex strip in the show notes, and what you can see is a 4-way or 4-point resistance measurement, and also a control measurement to see if there's enough blood wicked into the strip to do an actual measurement. Now, the way it works, basically, and I'm not really chemically educated, so I don't really know what's going on in detail, but there's an enzyme that the tip of the flex PCB is coated or saturated with an enzyme that reacts with the glucose in your blood, and it produces a substance that you can measure using a current measurement. So from the level of glucose that reacts with the enzyme and forms that substance that you can measure, you know the glucose level in the blood, basically. I'll post some pages with more information than what I just said in the show notes. And maybe it's quite interesting for you, because I didn't really know how that worked. Still don't know how it works really in detail. Also, maybe you may have remembered from biology lessons, if there's an enzyme involved somewhere, temperature is a critical factor. And to compensate for differences in temperature while measuring, the device must, I think, also have a temperature sensor on board. So there. Now on to some more environmental stuff, in this case fuel consumption of a car. And of course, not talking about electric cars. Electric cars are nice, and I'm planning to have one day, but right now it's a little bit outside my budget. But let's talk about fuel cars, fuel consuming cars. Over here I'm often thinking how to make people consume less, and also how to make myself consume less. One way to do that is to consume less fuel. What I came up with, and this is what follows, is basically secondary school physics, so don't fall asleep please. And what I came up with was that if you drive slower, it can save half in fuel cost, and it was a bit surprising for me. So on a recent trip, decided to drive back not on the freeway but on urban ways, and I estimate an average speed of 60 kilometers per hour there, because some roads here are maximum 50 kilometers and some roads are 80. So I estimate the average velocity of 60 kilometers per hour. While on the freeway the maximum speed is 100. The urban way that I took was approximately 10% shorter than the freeway between the 2 points. And the fuel cost for the urban way was approximately half. So it was 13 euros compared to 23 euros. I didn't actually measure how much fuel I put in the car, but I did the back of the envelope calculation, so sorry if it's not correct, but I think that's pretty much how it is. So the way that works is, let's say you have a car driving in a vacuum on a frictionless road. Then once you accelerate the car up to a certain speed, you don't need to input any more energy. The car simply will keep on driving at that speed. But in real life, you're not in a vacuum. You're not on a frictionless road, so you have wind resistance and you have rolling resistance. Wind resistance is pretty obvious what it is. Rolling resistance is the phenomenon where the car tire is continuously deformed. So as it rolls, the one part of the tire, namely the one touching the road, the side touching the road, is a little bit flatter, and you continually basically have to input energy to deform that tire to do that. Now if you take a look at the ratio, the fuel ratio between overcoming the rolling resistance and the wind resistance. Now with the example speed of 60 kilometers per hour, the rolling resistance is approximately the same as the wind resistance, so each take half the fuel needed to keep the car rolling. But if you take the car up to 100 kilometers per hour, which is not that much more I guess, the wind resistance is already more than 3 times the rolling resistance. And the rolling resistance was a constant. Now, of course, if you go faster than that, then the ratio between wind resistance and rolling resistance becomes bigger and bigger and bigger. Now, I'm not assuming all of you, after listening to this podcast, are going out to get a new car because of this, but let's say you are going to get a new car. There's some obvious things that you can take a look at if you care about the environment and not 100% only care about what your car looks like. So first of all, you might want to consider a light car, especially if you drive in an urban area. Especially if you drive in a city center where you have to accelerate and brake all the time. Because the force you needed to accelerate the car is proportional to the mass of the car, and also the rolling resistance is proportional to the mass of the car. And remember, the slower you drive, the more impact the rolling resistance has. So the more fuel goes into overcoming rolling resistance compared to wind resistance. So it becomes more important when you drive slow, let's say that. So choosing a light car, you can win a factor 2 basically compared to a heavy personal car. And one really easy fix you can do to lower the rolling resistance is to keep your tires inflated. Now I don't think it's that spectacular what you can win. It's probably 10% what I could find on the internet, but it's a really easy fix. So keep your tires inflated so you save on fuel. And also you might want to get a streamlined car, especially when driving on the freeway, because on the freeway, when you drive fast, the wind resistance becomes much more important, so everything you can win there is nice. And what I came up with was also roughly factor 2 between the smoothest car and the bulkiest car. So maybe you want to get a light, smooth car, light, streamlined car. That was a little bit preachy, I guess, but if you don't like it, or if you do like it, let me know using email. An email address you can find at the podcast.cba.si page, as usual. Next up is a little bit about a handheld oscilloscope I bought, a dual channel oscilloscope. Now, if you're a faithful listener of this podcast and you listen to episode 19 of many, many years ago, I guess, there was a segment about handheld oscilloscopes. Now, I've only tried a few of these, low-end ones, and my personal conclusion back then was there are some really nice things around, but they were outside of my budget, and outside of my budget back then was €400. Now, prices have been lowered drastically, so I finally bought one, and it was the OWON HDS242S, which is 40 megahertz dual channel scope. It's about the form factor of a Fluke multimeter, and it has indeed a multimeter built in. And it also has a function generator built in. Now, I don't really need a function generator, but this was the only model that was available back then. So the price difference was not that much, so I got this one. The multimeter is useful, I guess. And it's not, I guess, doesn't really hold up to a Fluke, but if you like what I said back then, at least that's my personal view, if you have a backpack and you have limited space, you will appreciate one device that has 3 functions, basically, or at least 2. So multimeter, I'll probably use this one then. This feels like a real oscilloscope compared to some cheaper ones that I had here. The update speed is really, really cool. It looks like a low-end Rigel oscilloscope or OWON oscilloscope, for example, in a handheld form factor. So I'm really happy with that. Now, I'm not going to talk I'm not going to talk too much about this, because Martin Lawton, I think he's called, has quite a nice review of this. And he goes through, there's a review on YouTube in 2 parts. One is about the multimeter. I'm not that interested in that, but it's maybe useful that he points out the flaws and the gotchas of the multimeter. The other part is about the oscilloscope, and you can actually see how well it behaves. I'm really, really happy with this. So maybe it's a tip for you. This was, I think, €140 or something like that, or 150. And you get an actual oscilloscope, and it actually works. And it's pretty nice. The software is nice, and I think everything simply works. So I'm pretty happy with it. Maybe a tip for you. Last topic for today was a vacuum cleaner that I took apart. It didn't work anymore, and that was caused by the cable which had worn out where it goes into the vacuum cleaner. Now, this was one of those vacuum cleaners, I guess every vacuum cleaner has that, I don't know. There's a spring-loaded spool that can retract the wire, the electrical cable. So the cable had simply worn out. So tip for you maybe, if you buy a vacuum cleaner, retract the cable all the way, then put some electrical tape or some magic marker indication 1 meter from where the cable enters the vacuum cleaner. And next time, only pull the cable out until the marker, so you save a little bit on wear and tear. While taking a look inside the vacuum cleaner, some things I didn't expect. One thing was, as a power supply for the logic inside the vacuum cleaner, the control, was a resistor dropper. And actually, it's not that strange, because in this case, resistor burned about 2.5 watts, but compared to 2000 watts that the vacuum cleaner normally consumed, it's really not interesting. And also, why was there logic inside the vacuum cleaner at all? Because this was a simple model with only an on and off switch. So the motor was either fully on or fully off. So it could easily be done with a simple electromechanical switch. But there was even a microcontroller in there. So I talked with a friend about this, and I did a little bit of searching on the internet. What I think is, this makes it possible to use the same PCB for different models of vacuum cleaner. For example, if you have a fancy model with 2-speed motor control, so you can have the motor at full speed or half speed, half power or full power, you can do that with a microcontroller, because there was a triac motor control in there, and in this model it didn't do anything. Triac was fully on or fully off. But that becomes possible then. And also you can do harmonic suppression. So if you do use triac control to run a motor at half speed, let's say that, you can add a little bit of jitter in the moment where the triac is activated or deactivated. So the emission, EMC emission of the motor becomes a little bit more friendly, because you basically spread out noise that the vacuum cleaner outputs over a range of frequency instead of noise always appearing at the same frequency. So I think it's a little bit of a trick to pass EMC compliancy. And also, I think there was I saw solder points on the PCB. Again, I don't have pictures of this because my phone was stolen, so sorry about that. But I think there was solder points on the PCB to have a button and LED interface. So there were some provisions to make a more fancier model or something like that. So that was essentially it. Thank you very much for listening. And some meta information about the podcast. Now, I think I mentioned this in the last few episodes already. My interest is shifting slightly from hobby electronics to other things, not having to do anything with electronics at all. So to be quite honest, I don't know when the next episode is going to be aired, but I think the hobby's coming back at some point. It's been like this before, but don't hold your breath. And thank you very much for staying with the show so far. So that was all for now. For more information, links and previous episodes, visit podcast.cba.si. Stay tuned, thanks for listening, and goodbye.